Graphing points, domain, and range. We're also going to talk about what makes an equation a function. So we begin with the coordinate plane. A plane is an infinite flat surface, and the coordinate plane is an infinite flat surface that we graph points on. It has two axes. The x-axis is the horizontal axis, and the y-axis is the vertical axis. The origin is that point right in the center. The coordinate plane is divided into quadrants. Quadrant 1 is where we spend most of our time, and we go counterclockwise. Quadrant 2, Quadrant 3, notice the Roman numerals, that's the way it's normally done, and Quadrant 4. When we graph in the coordinate plane, we graph ordered pairs that make lines and curves. An ordered pair consists of a x and a y. Notice that it's always alphabetical. So this is the point. X is 3, x is always first, and going up, y is 3. Over here is the point where x is -4 and y is 1. Here's a point where x is -6, x is always first, and y is -2. And in quadrant 4, I'm going to give a point that where x is +1 and y is -7. All the x values together make up what is called the domain. All the y values make up what is called the range. The independent variable is the input variable. And the dependent variable is the output variable. Now, note something here. The domain is the x values. The independent variable is the actual variable x. So it's different because the domain is a whole bunch of values, and x is the variable itself, is the input variable. It's the independent variable because we plug anything in we want. The range is all the y values we get out of an equation, but the variable itself is called the dependent variable because what we get for y depends on what we put in for x. Let's take a look at a line, y equals 2x minus 1. This is a linear equation, and it will produce a straight line. So I can pick any x values I want. I could pick -2. I could pick 0. I could pick 1 or 3. Anything I want. X is the independent variable. All these values here are called the domain. Let's plug these values in. The first one is 2 times -2. I'm plugging in -2 minus 1. 2 times -2 is -4. -4 minus 1 is -5. The next value I plug in is 0. 2 times 0 minus 1. That's what y is. 2 times 0 minus 1 is 0 minus 1, which is -1. If I plug in 1, it'll be 2 times 1 minus 1, and y will equal 2 minus 1, which is 1. Plugging in 3 would be 2 times 3 minus 1, which is 6 minus 1, and y would equal 5. So I'll graph these. Remember, it's always alphabetical, x first. X is -2, y is -5. X is 0, y is -1. X is 1, y is 1. X is 3, and y is 5. These values are the values in the range. And the y variable, remember, is the output variable, the dependent variable. What we got for y depended on what we put in for x. Y is the dependent variable, x is the independent variable. All the values that I plug in are the domain, and the values I get out are the range. Look at the line. Notice those points. If I pick new values like 4 or -1, all those points will be on this straight line. That's why we graph a line. What it is every solution to an equation. When we graph the line, we put arrows on each end because this identifies the line continues forever. It is infinite in length. If you were asked to graph x plus y equals 1, you could just think of two numbers that add to 1, like 1 plus 0. X could be 1, y could be 0. Or 2 plus -1 would be 1. X could be 2, y could be -1. So you could come up with all kinds of numbers that work here. But usually what we're going to do is get y by itself because that makes, in general, an equation easier to work with. And then we can see the input and the output very easily in one equation. If we get y by itself, we have to eliminate the x. Now, we don't completely eliminate it. What we do is we move it to the other side. But hang on a sec. You can't just move it. We have to subtract it from both sides. What we do to one side, we must do to the other. Now, you could say y equal 1 minus x, and that would be perfectly okay. Note that you can't subtract 1 and x. They're not like terms. Or if you like, and this is where we'll be headed, you could put the x in front of the 1. Then, instead of 1 minus x, it would be -x plus 1. Note, these are the same. See, in the top equation, x is negative, minus x, and 1 is positive. And in the bottom equation, -x plus 1, x is negative, y is positive. If I were to make a table for this, remember, I can choose any number I want. X is the independent variable because I can choose any number. I could choose 3, I could choose 4, I could choose 0, I could choose -1. What I get out, the output, will depend on what I put in. Y is the dependent variable, so I'll plug in 3. -x plus 1 would be -3 plus 1, which is -2. I'll plug in 4. When I put in 4, it becomes -4 plus 1, which is -3. When I put in 0, it's the opposite of 0 plus 1. Well, opposite of 0 is 0. 0 plus 1 is 1. And when I put in -1, it's the opposite of -1. Notice the signs are separate. It's the opposite of -1 plus 1. The opposite of -1 is 1, and 1 plus 1 is 2. And then I'll graph these real quick. X is 3, x first, horizontal first, y is -2, x is 4, y is -3, x is 0, y is 1, x is -1, y is 2. Notice again, these are all on the same line. This is a linear equation. Every point on that line is a solution to the equation x plus y is 1. A little bit more about domain and range. Domain and range are called a set of numbers. In fact, what you see here, these are called set brackets. The domain and range are a set of numbers, and when we list them, we normally use set brackets. If you're given a graph and you're asked to list the domain and range, take a look at our graph. We'll go left to right and we'll list all the x's. So for this point on the left here, the x is -6, and I'm going to use a set bracket, -6. The next point, there's two of them right here. The x is -2 for both of those points. I do not need to list it twice. Either a number is in the domain or not in the domain. It's not in there twice. Going left to right, our next point is 2 for x, and then 4, and our last x is 5, and then we close our set bracket. The range is a set of y values, so we'll use our set bracket, and from bottom to top, our y here is -4. The next y is -3. The next y after that would be one of these two, and that would be +1. Again, 1 is not in there twice. It's either in or not in. The next y would be 3, and our last y is 5. And that's how we list the domain and range for a bunch of points. Now this would be the same thing if it was just a table. If they gave you a table and said list the domain and range, you take the x's out of the table and list them in set brackets, and you take the y's out of the table and list them in set brackets. The last graph was a set of points. When you have a limited number of points, a finite number of points, the opposite of infinite, it's called a discrete graph. We can list them all. There's a limited number of points, discrete. In this curve, there are an infinite number of points because between any 2 points, there's another point. So it's not possible to list them all, but there is a way to write down the domain and range. And later on, you will learn a way to do that with set brackets. But for now, we're just going to do a simple inequality to do this. So the domain is a set of all x. And my x's are between two numbers. Look at the x-axis. They run from right here to on the right side there. And we're running between these two values. So our x's are greater than some number and less than some number. And in fact, they can be equal to. Notice the solid dot that was black and the solid dot that was blue. So my smallest x is -6. And notice the open side is towards the x. All my x's are greater than or equal to -6. But see how the point is towards the x? They are less than or equal to, on the right over here, look at the x, 5. So my x's are between -6 and 5, and they can be equal to those numbers. And this is how we will write it when it's a curve. The range, the set of all y values, notice how we're using the y variable instead of the x, and they're between two numbers. Now we're looking at the y-axis. Now you're going to want to look at the point, but that's not what you do here. The lowest y value is right there. The lowest y values run from here clear up to here. So the lowest y value on the curve is -6, and the largest y value is 4. So we're looking up and down at the y-axis. What is the lowest y? What is the greatest y? And all my y's are greater than or equal to -6 and less than or equal to 4. The last thing we're going to talk about today is what makes an equation a function. Now this will seem abstract, but I'll explain it in simple terms. Each x value must have a single corresponding y value. Or another way you'd say it, that'd be more mathematical, is each element in the domain must have a single corresponding value in the range. Let's take a look at why this is important. If I want to track anything in real life, time and population, time and distance, let's say here in this case, I'm talking about maybe the world record marathon. So these points represent the runner's position. At 15 minutes, the runner was between 3 and 4 miles. At 30 minutes, between 6 and 7. Well, then suddenly in 60 minutes, there's 2 points. In order for this to happen, the runner would have to be in 2 places at once. That doesn't make sense. There can't be 2 distances for a single runner if I was tracking how far a person had run. This is true for anything. If this was population, I couldn't have 2 populations for a particular time. Anything we graph, we want there to be, for every x, there must be a single y. So we're okay until we get to right here. You can never have points stacked on each other when it's a function. And functions are what we use to represent things in real life. Every x must have a single corresponding y value. In a table, this looks a little funny. If 3 went to 5, 4 went to 7, and 4 went to 8, in that case, 4 has 2 values that it goes to. You're going to end up with a graph that has points on top of each other. Every single x does not have a single corresponding y value. This is not a function. In graphs, whenever you have circles, ovals, or curves where you can draw a vertical line through them and hit 2 points, it's not a function. The rest of these are just questions from your assignment. If you do your assignment and have questions, come back and look at the examples. Here's question 1. I'm going to write the ordered pair for A, which is in quadrant 4, by the way. Reminder, 1, 2, 3, 4. A, x is always first, x is 1, and y going down is -5. Always put parentheses around your ordered pairs. B is in quadrant 3, x is -3, and y is -4. C is in quadrant 1, x first would be 3, and y would be 4. D is in quadrant 2, x is -1, and y is 3. To complete the ordered pairs below, take and plug in each corresponding value. Notice that this is x, this is y, and this is x. So the first equation is y equals 3 times 6. Because x is 6, it's y equals 3x. So I get 18. The second equation, notice they give me a y. So take the original equation. It's 24 equals 3x. 3 times what number is 24? Well, that would be 8. You could also go over here and solve. Remember your equations and just divide both sides by 3 and see that x is 8. For the last point, x is 2, so y will equal 3 times x, 3 times 2. Y is 6. Question 9. Y is the opposite of x plus 5. So here, y is the opposite of x plus 5. Y will equal the opposite of 1 plus 5, which is 4. This was an x. Now they've given us a y. So we'll take our equation and we'll put in y as 8. 8 equals the opposite of x plus 5. Let's solve that. Get x by itself, subtract 5 from both sides. And now there's a 1 in front of that x, so it's a -1. Divide by -1, and x would be -3. For the last one, they give us an x of negative 2. So y equals the opposite. Notice the opposite in front of the x is separate from the sign on the number. Plugging in negative 2 for x plus 5. The opposite of negative 2 plus 5 is 2 plus 5, which is 7. Let's complete the points first. Y is the opposite of x. Y equals negative x. So this first one, y equals the opposite of 0, which is 0. For the second one, it's y equals the opposite of 1, which is negative 1. Notice how these two coordinates are opposites, 1 and negative 1. And for the third one, they give us the y value. So our equation, y equals negative x, is going to be negative 2 equals negative x. And I'll divide by negative 1 to find x, and x is 2. Again, notice how 2 and negative 2 are opposites. Plot your points. 0, 0, 1, negative 1, and 2, negative 2. And you'll be drawing a line that goes through those points. You just need 2 points to do that. X plus y is 3. Well, we know this would be 3 plus y is 3. 3 plus 0 is 3. This next one would be 5 plus y is 3. And I'll take a 5 off each side, and I see that y will equal negative 2. 5 plus negative 2 is 3. For the last one, they give us the y value. So our x plus y equals 3. I'm going to plug in y as 5. X plus 5 is 3. So x, if I subtract 5 from each side, would be negative 2. Plot your points. 3, 0. Notice I go up 0. 5, negative 2. And negative 2, 5. So when you draw your line, pick 2 of those points and draw your line. X minus y is negative 3. So x is negative 4. That's negative 4 minus y equals negative 3. Let's go over here and solve that. I'll subtract or add 4 to both sides. Negative y equals 1. And divide by negative 1, and y will equal negative 1. Another thing we could do that would make this easier, and I did this in the teaching part of the video, we could take this equation and solve for y. X minus y equals negative 3. Take an x off each side, get y by itself. Eliminate the x, move it to the other side, and I'm going to put the x in front. So minus x, negative x goes in front, minus 3, negative 3. Now I'll divide both sides and everything by negative 1, and y will equal x plus 3. Now this equation and this equation are the same exact equation. One's just easier to work with. Let's try this. Y equals x plus 3 becomes y equals negative 4 plus 3, which is negative 1, just like we got. Y equal x plus 3 is negative 2 plus 3, which is 1. And on this last one, they give us the y value. So we're going to plug in negative 2 for y, be negative 2 equals x plus 3. And if we subtract 3 from both sides, we see that x is negative 5. Let's plot the points. Negative 4, negative 1. It's right here. Negative 2, 1. And negative 5, negative 2. So use 2 of those points and draw the line. Again, we could solve for y if you wanted to. To get y by itself, you divide both sides by 2. Remember, there's a 1 in front of the x. That's y equals 1/2 x, or turn it around, 1/2 x. So if y is 1/2 x, then y would equal 1/2 times 2, which is 1. Y would be 1/2 times 4, which is 2. And here I'm going to put in y is -1. And maybe that would be easier in this equation, x equals 2y. If I plug in -1 for y, I get x is 2 times -1, so x would be -2. 2, 1, 4, 2, and -2, -1. Use 2 of those points and draw your line. Here's a question about domain and range. All the following are true except one. Identify the false statement. The domain is associated with the independent variable. Domain is x. X is the independent variable. That's true. The range is associated with the vertical axis, which is y. That's true. The domain is a function of the set of all possible values for the input. Domain is the input. That's true. The domain must include all real numbers. Now think of the points. Do you remember the graph where we did the points and it was just a few values and the set brackets? All real numbers refers to every number that exists. Positives, negatives, fractions, decimals. The domain doesn't have to be every number that exists. This one is not a true statement. It could be, it often is, but it does not have to be. The last one, the range is a function of set of all possible values of the output. The range is the output. This question uses some notation you may not have seen before. That's the f of x function. F of x is just another way to say y, so ignore that for now. We're going to talk about that in a day or two. But we're just talking about a function that's x and y, and we're going to write the domain and range. Domain are the x's, so we're looking at the x-axis right here, 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 all those. So we use curly brackets because those are set brackets. It's -9, -5, -1, 2, and 7. The range are the set of y values. So we're looking at the y-axis this time. Start at the bottom here. -9, 6, -1 for y, 2, and 6. This one's easier than the last one. Again, remember that f of x is just another name for y. Don't worry about that. The domain are the x's, so we use set brackets and we just list them. -14, -13, look at the x's, -4, 24. The order does not matter. It's either in there or not in there. The range are the y values, so we're looking at the y values. Remember, this is just y. 13, 55, 47, 99, 36, and 26. Question 18. This is like the one I did in the teaching part. There are infinite points on this line because between any 2 points, there's an infinite number of points. So we have to list it as with an inequality. They are showing us here how to do that. Look at the x's, look at the x-axis. The x's run between these two numbers. Notice the open circle on the -2. So my x's are all greater than, not equal to, greater than -2, but they're all less than, see how the point is towards the x? They're all less than 2. Look at the x-axis. Between -2 and 2 are my x's. I just noticed I nearly missed something. See the solid dot there? It can be equal to 2. The y's in red are between two numbers. Look at the y-axis, up and down. They run from 0, and the open circle means they can't be equal to 0, all the way up to 3, but they can be equal to 3. These are very quick once you understand. Look at the x-axis. For the domain, the x's run between here and here. Notice the open circle. So my x's are all greater than or equal to, because of the solid dot, they can be equal to -3. But the open dot on the other side, the x's all have to be less than 2. For the y's, they're between two numbers. The y's run from here. Now, not at the dot. You're not looking at the dot. You're looking at the curve. The very largest y is up here. It's 4, and it can be equal to 4 because that goes clear up to 4. And down at the bottom, it's got to be greater than -5, and it can be equal to -5 because of the solid dot at the bottom. This question is a quick one too. This goes back to what makes a function. Every single x must have a single y. So when I look at the graphs, I'm looking at the x-axis and asking myself, as I go up and down, is there always a single y value? This one is a function. Every x has a single y. Look up and down. For every single x value, is there a single y value? This one is a function. This one is not a function because there are x's that have more than one y value that corresponds. This one is a function. This one is not a function because of this situation. There is an x, that's 4, that has two different y values. It's like the runner. It would have to be in two different places to have two different distances. That doesn't make sense. And this one is a function because every x has a single y. The simplest way to tell that it's not a function is the vertical line test. If you can draw a vertical line and hit two spots, it's not a function. That is not a function. Not a function. So the functions are these ones here. With the table, there is a way to tell fairly easily that it's not a function. When you look at a table and you see they're all different x's, you're good. It doesn't matter if y's get repeated. Every x just must have a single y. So even this one over here is okay. This is okay because every x goes to a single y location. Yes, 2 gets repeated, but 3 goes to a single number 2. And 4 goes to a single number 2. That's okay. This one is not okay. And the reason it's not okay is there's a single number. You're seeing 2 of them, but there's only one. That's the number 1. And that 1 goes to 2 different locations. This is not a function right here. All the others are functions because every x has a single y. The easy way to tell in a table then is if you see x values that get duplicated, be suspicious that it's not a function. Look at the numbers carefully.